Hey everybody, welcome back. This is the second part of chapter 22, dealing with immunity. Today we're going to cover the specific defenses or the adaptive immunity system or adaptive immunity. And so don't forget that this is something that is not you're not born with. This is created upon exposure. So you first have to be exposed to a new antigen, and then the body is going to respond by creating a specialized specific type of defense. And we're going to see that this is truly your true immunity and your most powerful ways of destroying things that are in the body. If we do not have our adaptive immunities functioning, if we don't have our specific defenses functioning, then something is going to overwhelm our body and it's going to kill us. And so, as I mentioned before, this is what we notice whenever we talk about HIV or AIDS. That virus will affect the specific cells that we're about to learn about that stimulate the T cells and B cells, the main fighters, the cytotoxic T cells and the B cells, to do their thing to fight the bad guys. So the helper T cells is what HIV targets, and it doesn't allow them to co-stimulate kind of other cells, and as a result, they never become active. And then an HIV patient tends to die of something like cancer or pneumonia as a result. So, very important, the adaptive immunities. And it's really the most powerful component, and that's a good part because it adapts to the new things that we see, right? Upon exposure. It takes longer to respond compared to our innates or our nonspecifics. Remember, the nonspecifics are always active, but if something to our body, the innates are thrown at it to kind of do damage control and keep the problem from getting worse as we build up our adaptive immunities. When we come in contact with a new foreign antigen, then we're going to see these lymphocytes are going to respond to this new foreign antigen. And then, as we see right here, one of the processes we're going to notice is that all of these T's or B's are going to start multiplying. They're going to form an army, and that army is aimed at just killing that one target with that foreign antigen. We definitely want to overpower the bad guy. We don't want to have a one-on-one. We want it to be an unfair fight in our advantage. So we always want to have as many of these cells as we can to help defeat the bad guys. Now, again, this is our true immune response, and I don't like this considered third line of defense. This is about stupid. This is our body's primary defense for true immunity. But because it doesn't kick in until after the skin fails and after our innates have tried their best, then this is when that kind of starts to develop. So they consider it a third line, but I think that's a really bad way to describe it. There are two components to this specific defenses or specific immunity. And you know what? Before we get there, let me give you another little fact, the kind of about the specific defense. And I've said this before. I want you to write it down in your notes one more time. That the specific defenses, they create a specific solution to specific problems. And this is really the most powerful response that we get, creating a specific solution to specific problems. Don't forget that the specific problem are foreign antigens, and the specific solution are going to be antibodies, especially, but also some of our cells that are combating that as well. And so, again, the specific problem is going to be a foreign antigen, and the specific solution tends to be an antibody. And that's our most powerful type of response, is to throw an antibody at it. So we've got two different groups of cells and two different types of adaptive immunity. We have cell-mediated immunity, and then we have antibody-mediated immunity, or humoral immunity. Here we can see that cell-mediated immunity is undergone by T cells, cell mediated with T cells. Humoral, humor means fluid, and that is triggered by B cells. So finding a cell that is abnormal, and that is, hey, so finding a cell that is abnormal, that's infected or cancerous. Sorry for that little snafu there. So finding a cell that's cancerous or abnormal, then these are the cells, these T cells are going to find them, and they're going to go attack them. They're going to find a way to destroy them. Humoral immunity, on the other hand, in a fluid, in a humor, either blood or lymph, we're going to trigger B cells, B lymphocytes, and once they find one specific foreign antigen, they become a new cell. And this is a very specific cell related just to producing the antibody for that antigen, and that is called a plasma cell. So an activated B cell becomes a plasma cell, and it's the plasma cells that actually release the antibodies. And the antibodies are kind of like heat-seeking missiles, except for instead of seeking heat, these guys are only seeking that foreign antigen. It's almost kind of like a hormone. We put it in there. If any cell has a receptor, has that antigen, then it's going to bind and it's going to destroy it. So here we kind of see some comparisons between the two. Let's just kind of jump into it. Okay, don't forget an antigen. First off, it is actually a scrap of a protein. It's a leftover piece of protein made by that cell. And so the key here is usually those proteins should be the type of proteins that that cell is supposed to make. Remember that the DNA in the nucleus codes for protein production. And so if it is a normal protein, we call it a self-antigen that appears on that cell. And remember, these antigens are just little proteins on the cell surface. They kind of identify it for the immune system. Our normal cells make our normal proteins, and those become what we call self-antigens. Our immune system ignores the self-antigens, right? So it does not want to react to a self-antigen because that's an indicator that this is a good guy. This is one of our own. This is not a foreign invader, or something that has mutated. If that cell is making weird proteins, then those weird proteins are demonstrated on that cell membrane. And if it's a protein that's not supposed to be made by our DNA, if it's not coded by our DNA, then our cells identify that and they target that. That's what we call a foreign antigen. And so this foreign antigen is not supposed to be in our body. It's not supposed to be coded by our DNA. And so that cell is either a cell that was once in our body and has been changed, it's been mutated, it's been become cancerous or infected, or we've got an invading cell in our body, right? And so the foreign antigens are what truly trigger the immune response. So our cells will identify, our T's and B's will identify these cells with foreign antigens. We'll go up and each one of these T's and B's will attack it differently. T cells like to be very physical, so they like to have more of a hand-to-hand combat, a cell-to-cell combat kind of situation where it's up close and personal. And the B cells instead, they like to do the smart type of war where they're going to sit in their organ, in their lymph node, and they're just going to make these antibodies that are floating all around, right, that are going to be able to kill those bad guys. Now, if for some reason our self-antigens become targeted as foreign antigens and our good tissues start to be destroyed, well, that's what an autoimmune disorder is. An autoimmune disease is the process where the normal tissue is somehow identified as a foreign tissue and then we start to destroy it. So rheumatoid arthritis is an example there where the cartilage is actually identified as a foreign antigen and the body starts to destroy its own cartilage and it creates that debilitating effect. Okay. Now the antigenic determinant, I'm not too worried about this. This is just kind of the binding site. The whole key here is that only certain antibodies bind to certain antigens. And so we can find these foreign antigens, and then we're going to start to build an antibody based on that. Again, we've already talked about these autoimmune disorders, so we're going to move on past that as well. Let's talk about these T's and these B's. Now, I like to separate these out, and I will try to give you another handout online that kind of gives you some steps of this because the way that they set these steps up, I don't like this. They group these together and they treat them to be the same thing, but T cells and B cells are a little bit different and they act different. And so I like to talk about them differently, okay? T cells and B cells, these are our two main specific defenders, our two main lymphocytes that we're going to be talking about. Again, the B cells, they can make direct contact with the antigen. And so we're going to talk about this here in just a second, how this is different. So B cells can come up and they can identify any antigen that they find in the body. But T cells, on the other hand, have to have the antigen presented a certain way. It has to be processed. So the antigen has to be presented on a certain way. It has to be held up by a certain hand off of the cell membrane for a T cell to identify it. And so this makes it a little bit more specific. So we're going to talk about this process. Now, no matter what, either T's or B's, First off, what we're going to do is we have the lymphocytes. We have our T cells and our B cells. Now, these cells are formed in our primary lymphatic organs, either in our blood tissue, in our bone marrow, where the blood cells are made, or in the thymus, and that's where T cells get their name, is in the thymus. And so these cells are then going to become activated whenever they find a foreign antigen. So activation of the lymphocyte involves these guys leaving their home and becoming exposed to that foreign antigen. When they become exposed to the foreign antigen, they must become activated in order to replicate, in order to build that army. The key here, and this is something that I want you to add a note about, anytime we're talking about this activation, this is always done by a helper T cell. Okay, so this activation is always done by a helper T cell. If we don't have the helper T cell there, then we never activate the T or the B cell, we never produce an army, and we never have a powerful response. And again, this is what HIV is doing to the immune system by limiting the effects of helper T cells. It limits the effects of the other T cells and those B cells. So then we don't really have a response at all. Okay. And of course, the response, like we said, is we need more than a good guy to fight the bad guys. We want to totally overpower them as much as we can. So we're going to build an army. So after activation, we're going to kind of replicate. We're going to create more of that same cell. It's going to divide. And there's something I want to mention real quick is when we replicate, I want you to add the term memory cells. Anytime we replicate one of these lymphocytes, we're going to put some in storage for our next response, for the next time we see that problem. Not for right now, but for a year later whenever we see it, for example. And those cells are called memory cells. This is, for example, why chickenpox, you can get chickenpox and then hopefully not have it ever again. You can be exposed to it, but you just won't have it in the body. It won't affect the cells. It's because the memory cells remember that, and it remembers it for a lifetime many times. Okay, right now this is something we're having to figure out about COVID. We're seeing reinfections that are taking place, and so this is part of the big issue with building a herd immunity, and why we may not be able to build a herd immunity until we have more time to see more people. If reinfections are possible, then that means herd immunity is never possible, because if you can become reinfected, then nobody is immune to it, and therefore we have no herd immunity at all. And so it's really tough. You got to listen to smart people, not politicians and not people that don't really know their stuff, because you hear that term herd immunity thrown around, and anybody that actually knows their information about this, they understand that here is the problem, that herd immunity may not be able to be built. And that's another reason it's taken so long to find a vaccine that's going to be extremely effective. Now, the third event in the life cycle is now we're going to have the effector response. The effector response is how we kill that target, right? We've identified this cell, it has foreign antigens. Well, now what can we do to kill it? As I said, T cells, they tend to go straight to the problem, they confront the bad guy, and they physically beat him up. Okay, we're going to talk about that. They're very similar to NK cells. They're going to release perforins, they're going to release granzymes, and they're going to try to kill the bad guy. B cells, on the other hand, they're going to hang out where they're located. They're not really going to move, and they're just going to start spitting out massive quantities of antibodies. And again, these antibodies are in the bloodstream and in the lymph, and so then they're going to get transported to the problem and hopefully bind and destroy that bad guy. Now, antigen challenge is also sometimes referred to as antigen recognition. I prefer the term antigen recognition. So with antigen recognition, this is simply just the first time that the lymphocyte encounters this antigen. And so this is when it starts to become activated, but it takes more than that. This is when it finds a foreign antigen. Okay, usually this is in a secondary lymphatic structure, something like the spleen or maybe in a lymph node, right? And so as a result, then we're going to start to trigger that immunity. We can call those T cells to fight hand to hand, cell to cell, but we can also start those B cells making those antigen seeking missiles, those antibodies. So the antigen challenge or the antigen recognition is always the first step. So if you want to keep track of this, you can put it on a little separate piece of paper. You can put T cell T cell processes and B cell processes. For each of these, the first is going to be antigen recognition or antigen challenge. And again, that first step is simply the same first step for both T's and B's when they first find that foreign antigen. Now, let's talk a little bit different about T cells and how they do this differently than the B cells. T cells have another step. They have an extra step after antigen recognition, and that is antigen presentation. If the antigen is not presented properly, and I mentioned this earlier, it's kind of like a very specific hand holding it up off of the cell. If it's not held up by that hand, then our immune cells can't identify it. And so T cells have this extra step called antigen recognition, but B cells do not have that step. B cells can go straight to being activated by a T cell, excuse me, by a helper T cell, because these B cells, again, can make direct contact with the antigen. They can come up and directly contact it. They don't have to worry about it being presented. Now, let's talk T cell stuff right here. Okay, so maybe we can just do kind of steps of T cell process or T cell activation. The first step, again, was antigen recognition. That's whenever it identified it or it noticed it. But this antigen must be presented. And so here in T cells, we're going to talk about these things called CD markers. So the CD markers are important for T cells only. These CD markers identify the different types of T cells. And I've kind of been talking about this. There's two main types of T cells. I'm going to switch these up. CD8 are cytotoxic T cells. The cytotoxic T cells are the cell-to-cell combatants. These are the ones that are physically going to enter a tissue and start to fight the bad guys, try to destroy them by spitting chemicals at them that will kill them. Toxic chemicals, right? Cytotoxic. So these are the true warriors. When I say a T cell kills a bad guy, this is the T cell I'm talking about. Make sure that you connect CD8 with him. You don't have to know any more detail than that. Just realize that this specific type of protein, this marker, this CD, is a CD8. The other major type of T cell that we're going to talk about are helper T cells. Helper T cells, these guys activate T and B cells. So without the helper T cell, we don't activate our cytotoxic T cells. They don't make an army. They don't have a fight. We don't stimulate the B cells to make plasma and then start to become plasma cells and then start to make antibodies. So as a result, without stimulation from a helper T cell, nothing is possible. Neither one of these two can do their thing. Helper T cells are identified as CD4s. Okay, CD4 cells, don't worry about the plus unless you just want to. CD8, cytotoxic, CD4 is a helper. Now, there's another one that I want you to be familiar with. There's another T cell called a suppressor T cell. Suppressor T cell deactivates T's and B's. And the whole thing is whenever we're trying to turn the response off, these suppressor T cells tend to get involved to turn the response off. Helper T cells are there to turn it on. Suppressors are there to turn it off. And so that's kind of the way that you can think about it. Now, again, these helper T cells, no matter what, these guys have to, let's kind of write this down. Okay, helper T cells, what they do is they kind of double check antigen and then give T cell or B cell permission to be activated. So they're going to double check the antigen, and after they double check it, then they're going to give permission to that cytotoxic T cell or that B cell to do their thing, right? So a lot of times I'll use that phrase double check, okay? Now, let's talk about this antigen presentation process. And again, this is only with T cells. When we're looking at these T cells must have the antigen presented. And this is what I keep saying. B cells can interact with the antigen directly, but T cells, on the other hand, they have to have it presented by that very specific hand hanging it off of the cell. We call that hand hanging that structure off an MHC. Major histocompatibility complex. This is the main tissue compatibility structure that we have to worry about. Now, major histocompatibility complexes, there are two different types of these. And again, these are the only antigens that a T cell can identify are ones that are held up by these MHCs, ones that are connected to the MHCs. Now, here's the way that we can think about it. The first group, MHC1, these are found on all nucleated cells. So these are the ones that we usually identify our own body cells as either normal or foreign. Okay, so far I've been talking a lot about how a cell, if it's making a foreign antigen, then it's a bad cell. It's been mutated. Something's wrong. This is the MHC that we're talking about. So most of these MHCs, either it's normal or it's foreign on that cell. That's an MHC1. If it's a foreign antigen, it triggers a response. If it's a normal antigen, a self-antigen, then it's just ignored. MHC2s, on the other hand, these are found on what they call APCs. An APC is an antigen presenting cell, and basically this is just a phagocyte. That's the way I want you to think about it. These APCs are phagocytes. So in other words, an MHC2 is displaying what a phagocyte ate. Okay, MHC1's normal cells. Is it normal? Is it foreign? MHC2s, though, a phagocyte ate something, and now the phagocyte is presenting it on its own cell surface. Okay, so first off, MHCs, like I said, these are your normal ones. So here's an example. We can just kind of see that some of these peptide fragments are made inside the cell. So these are just leftovers from whatever that cell made. It's going to get processed through the ER and then through the Golgi. And here we can kind of see in that process, here's that MHC molecule. Kind of looks like a weird little lobster or something. But what it really acts like is once it gets up here, is it kind of acts like hands, right? Here you can kind of see this cupped hand holding that antigen off. Here we have a self-antigen, and so that means we're going to leave it alone. But if we had an antigen that was foreign, then it's going to trigger a response. So here we have this bacteria or this virus that has came in, and so now it's infected our cells and it's making these weird peptide fragments with viral particles. So now that MHC1 is going to grab it, it's going to float it to the surface and display whatever antigen is being made, whatever protein is being made inside that cell. And here we can see now it's a foreign antigen. So this is going to trigger a response compared to this one back here, where it was a self-antigen and it did not trigger that response. Okay. Now, MHC2s, again, this is in a phagocyte. A phagocyte eats it, it's brought into the cell, and then it merges its lysosome, so it breaks it up, and then it takes that MHC2 and it loads those fragments that the phagocyte broke apart inside of its body. It loads some of those onto that MHC and floats it to the cell membrane, and there it's kind of telling us what's up. Here's the bacteria. The phagocyte ate the bacteria. It's merging its lysosome. The lysosome is the stomach, so it destroys, it chops it all up. But here we can see those little antigens on the surface, right? And so it chopped them up. Now we loaded it onto this MHC2. We floated it to the surface, and now it's demonstrating here. I engulfed this bacteria. Come kill me, right? I've got too much bacteria. This could be dangerous. If it's normal cell debris, then it should just have our own normal antigens on it. So that shouldn't trigger a response. So again, MHC2s in phagocytes. All right. Now, with each of these, again, with T cells, part of that antigen recognition, we had to have the antigen presented first properly. So it's really kind of like step one is antigen presentation, and then in step two, it's antigen recognition. And here, this is kind of the step of antigen recognition for both T's and for B's. So with both of these, the antigen recognition is simply when the T cell or the B cell first encounters the foreign antigen, and then it needs to be stimulated, right? It can't become active automatically. If we have cells that don't have to have permission to become activated, then they might go overboard. They might start attacking tissues that don't need to be attacked. So the activation here, the T cell first finds the MHC molecules, and then it binds to it, and it kind of hangs out right there at that antigen, and it waits. So the next step in antigen recognition, it found it, and then we're going to move to we're going to move to lymphocyte activation. Okay, that's going to be our step 3 in T cells and kind of step 2 in B cells. Anytime we talk about activation, this has to do with the helper T cell. So the helper T cell is going to find the problem. It's going to come up and meet with that cytotoxic T cell that has found this bad guy, and the helper T cell is going to bind as well. Anytime we talk about lymphocyte activation, we're always talking about helper T cell is going to double check the antigen. And after it double checks the antigen, if it is a foreign antigen, then it activates that cell. So here in the T cell, we first had to have it presented on an MHC. Then the T cell recognized what was on the MHC, a cytotoxic T cell did, and also a helper T cell. And so that helper T cell identifies what's on there, and the cytotoxic T cell does too. The helper T cell, after it identifies the antigen, it starts to become activated and it makes memory cells and it makes extra helper T cells. And now these extra helper T cells are then going to go and help to stimulate the cytotoxic T cells. And so the key here, the cytotoxic T cells are going to make contact with this MHC molecule, and then the helper T cells are going to cause the main stimulation. And this main stimulation activates the cell. Anytime we have a helper T cell doing its job, it activates the T or the B cell. So now we have activated cytotoxic T cell. The helper T double checked, and now it gave it permission. And so now this cell is going to start whooping some booty. So now we make an army. So the cytotoxic T cells are going to divide. We're going to create the army with the activated cytotoxic T cells, but then we take some of our army and we put it back in memory. So we have memory cells as well, and the memory cells are for the next exposure, re-exposure. And that way, if we have enough memory cells, we can immediately see that problem and destroy it before it can even get a hold inside of our body, which is very important. Okay, now, again, here's what happens with the B cells. The B cells, first off, they identify that antigen. They're hanging out with that antigen and they're waiting for that second stimulation. They're waiting for the helper T cell to come along and to stimulate them to say, yep, you found, I've double checked, you did find a foreign antigen and you are right. You need to multiply and make your army. So the army is not called an activated B cell. It really is, but we now call it a plasma cell. The word plasma cell is an indicator that this B cell has already become activated and he is actively making antibodies, he or she, right? And so a plasma cell is really an activated B cell that makes antibodies. But again, we multiply, we divide. That really just means that we're making more copies. We're multiplying, really. And so now we've got an army of plasma cells, just like we did with our cytotoxics, just like we do with our helpers. Now we have memory B cells as well. Okay, so I didn't mention that, but back here we also have our memory cytotoxic T cells, right? I think maybe I did mention that, sorry. And that's for our next exposure, but same thing. Now, whenever we see that problem again, instead of having to do the antigen recognition, the antigen presentation component, and become activated by a helper T cell, now we are already activated. These memory cells are already activated. So we short circuit the response anytime after the very first response, the primary response. Any secondary responses are faster and they're more powerful because of memory cells. Very important. Okay. I don't want you to look at these pictures. These pictures can be quite confusing. Now, we've already got our activated T's and we got our activated B's. Now, our last stage is that effector response, right? So how do these things kill their bad guys? Don't forget cytotoxic T cells. They're physically going to come up and have hand-to-hand combat, cell-to-cell combat, and force apoptosis. They're going to trick the cell into killing itself, right? Apoptosis is that normal cell death. But if this cell can kind of do the old Jedi mind trick and say, you want to kill yourself, and then the bad guy says, I want to kill myself, and he kills himself, right? The unhealthy cell just self-destructs. These plasma cells, these activated B cells, now start to make those antibodies. So let's talk about each one of these just real quick. Here's what happens with our T cells. When we activate a T cell, and we keep our memories, but then the activated T cells, what can they do? They destroy cells. How do they do it? They release perforin and they release granzymes. Now, if you remember, this is exactly like our NK cells. Go back, re-listen to that. This is the exact same thing. Perforin pokes holes in the bad guy's membrane, and granzymes are the thing that trigger self-destruct. So first, we're going to poke holes in it, let it start bleeding out, let it start oozing out, and then we're going to slip some of these old Jedi mind tricks in there, these granzymes, and these are going to go in they're going to tell that cell you want to self-destruct, and so then it triggers its own death, which is called apoptosis. Okay, and this is what we call cell-mediated immunity. That T cell mediates the immune process. Okay, here they're building the pore and they're putting the granzymes in, and then it just kind of kills itself. It just kind of oozes out. B cells, on the other hand, they're going to create plasma cells. And these plasma cells, again, are going to make antibodies. And so we'll talk about these antibodies real quick. Antibodies are the most powerful response that our body has. We can produce millions of antibodies during a 5-day lifespan. So it doesn't take very long for this one plasma cell to make millions of antibodies, and that's pretty powerful, right? Antibodies are circulating through the fluids, through the blood and the lymph. That's why we call it a humoral defense or humoral immunity. And don't worry about the term titer. This is just kind of how much concentrations in the bloodstream. Not too concerned about that. Let's talk about this. We've only got about 10 or slides left, so we're kind of on the downhill slide with this. We're going to wrap up these antibodies and then maybe talk just real quick about some of our basic immunities, and then we will get past a couple of patho examples, and then we'll be finished. So here, antibodies. Again, antibodies are also referred to as immunoglobulins, right? That's why we see this abbreviation IG many times. IgG, IgM, IgA. The IG means immunoglobulin, right? And these were one of our plasma proteins. These are shaped like that giant letter Y, right? And so these guys are going to do all kinds of responses, but we'll find out here in just a second kind of what's the big deal with them, right? Each antibody looks like a big letter Y, right? The very tips of the Y, I want you to know the ends of the Y here, okay, these are called the variable region. This is what changes between all of the antibodies. We're going to have 5 groups of antibodies. We're about to talk about those. The 5 groups are based on this part that doesn't change, called the constant region. But what keeps changing based on each individual antigen is the variable region, and that just makes sense. It varies. And so at the end of the arm, we see the variable region, and at the very tip of the variable region, we have what binds to the antigen binding site. So the tips of the Y bind to the antigen, and they're going to trigger some sort of destruction process, and we're going to talk about that. Now, as I said, the constant region, we have 5 groups of these. So there's constant shapes that don't change. There's 5 shapes that don't really change, and each one gets its own group. So here, in just a second, we're going to talk about those 5 different classes. But the key, these antibodies, these guys are the strongest type of defense, our humoral immunity, strong against bacteria or viral particles. Right now with COVID-19, we're really concerned about viral particles. Toxins, these are poisonous chemicals that are made by these cells, or maybe yeast spores. So these things are very effective against the main infectors in our body. Here's our 5 classes: IgG, IgE, IgD, IgM, and IgA. Let's start with IgM. IgM is the first to be produced during a response. This is what we call a 5 antibody starburst. I love that phrase starburst, mainly because I like the candy. But to be honest with you, think about this. If we took 5 of these letter Y's and we linked them in a ring so that now the branches, the arms of the Y are all facing out. It almost looks like a snowflake, kind of, right? A starburst looks like a star. And so this is IgM. This is the first to be made. This is kind of like a Swiss Army knife. It's not the best knife, but it can get the job done, right? This is the first made because it's got the most variety of antibodies that can help with the situation. Now, the main antibody that we're shooting for are IgGs. So the IgG is the main one. This is the most common. These are the main effective ones. But what happens is before we make the true IgG, the one that's going to be the most effective, well, let's make something that can help us do a little damage control before then. And so we can throw this 5 starburst, right? It's got 5 different antibodies. Maybe one of those 5 will help. But then as we get the actual one that we really need a knife. That Swiss Army knife will work for a while, but if you've got a really good fixed blade knife that's about 5 inches long, well, now you've got the blade that you really need, and that's that IgG, right? So we're trying to whittle down a piece of wood. It sucks trying to do it with a Swiss Army knife, but if you got a real, kind of good knife, then you can whittle that that stick down pretty quick, and that's kind of the concept. So once the G's start to get more concentration, then the M's start to go away because the G is the more effective type, right? So little damage control, and then the main one. Then we got some specialty ones. IgE are involved with allergic reactions. IgD help activate B cells. IgA are found in secretions, glandular secretions like your tears and your saliva, right? Why is it that sometimes you cut your finger, you put your finger in your mouth? Are you a vampire? You could be. I'm not doubting that. But more than likely, it's because you naturally know that there's antibodies in your spit, in your saliva. And so you're kind of putting it in your mouth. Same thing with your dog. If you cut your finger and they see that, many times a dog's going to come up and lick on that cut because they know that naturally they've got this antibody in there. They don't realize it, but this is why they're doing it, right? And so they may lick your finger to try to help you out as well. Here's a little table 22.6 in the textbook discussing those antibodies if you'd like to look at those. Now, real quick, initial primary response. This is the first time that we see the bad thing. So the primary response is the first response. Usually this is a longer and less powerful response compared to future responses, compared to secondary responses. So the primary response, the first time we see it, it takes a long time to build the defense. And it may not be as powerful. We don't have as big of an army as we are on our second try. And the reason why is we have something called the lag or the latent period. And this is just when that detection, this activation and proliferation is taking place. When these cells are starting to build their army, it takes 3 to 6 days. And so now that we finally get the antibodies produced in about a week or so, now we can get those levels up and that can start to defend the problem, right? So it takes a while to build the defenses. So the primary response, it's slower, not as powerful compared to the secondary response. Remember, we've got memory cells. Memory cells are what we're going to use anytime we have that antigen exposure again. Anytime our body finds it again, we're going to go ahead and have this memory cell kick in, and now we're going to have our secondary response. Again, that memory cell is already at activation, so it can short circuit that lag phase and jump start the whole process. It eliminates the lag phase, and so now it is a stronger and more powerful response as a result. So it produces a more powerful response, and the levels of antibodies rise more rapidly. And so this is going to give us a more powerful type of a response. Now, we've already talked about this previously, but I will mention this again, active versus passive immunity. Active immunity, remember, is when you're exposed to the antigen and you produce your own antibodies. We can have a naturally active process, and that's what we do every day by walking around in nature and just getting exposed in our classroom or out in the workplace or wherever to whatever antigens that we need to fight against. Or we can have an artificially active immunity, and this is where we are injected with an immunization or a vaccine. We're given a dead or an active version, an inactive version of that problem. All that we need are just foreign antigens. So it doesn't have to be an active bacteria or active virus. All that we need are just their antigens. So we can even chop them up and make what's called antigenic fragments. And so we inject these antigens into your body. It causes a primary response. And then that way, anytime we actually see that disorder after that, we just have a secondary response, like the flu vaccine, right? Very important. It gives you a primary response. And then when you finally see that flu bug, then you have a very powerful secondary response and you don't really get sick to it, right? Now, again, we make memory cells with this. Passive immunity, we're simply giving antibodies. So instead of giving the antigen and then producing a response, we're giving the response to the person. Naturally passive, you can get that through mama, through the breast milk, or through the placenta. And so this is how mama passes some of her antibodies so that baby has, fetus and baby have their own little immune reactions. And so very important, especially in the very beginning of a child's life, right? Because they're born, if they have no defenses really, then they're going to be in big trouble because things could take their life very easily. Artificially passive immunity is where someone gives you antibodies, an injection of antibodies. This is more common whenever we talk about antivenom. So antivenom is a form of an antibody to that toxin from the snake. And so, for example, snake or spider, and so antivenom is a good example of that. Okay, neither one of these make memory cells. So again, this is not really triggering a true response. It's just kind of handing off those antibodies. Again, vaccinations, dead, weakened version. And so it stimulates B cells to start making those antibodies, and then they're just found all throughout the bloodstream. Hypersensitivities, allergies, and allergens. We kind of talked about this also at the end of that last presentation. But again, an allergy is a hypersensitivity, and it's an overactive immune response. It's another way to think about it: overreaction of the immune system, and the allergen is what causes it. Anaphylaxis is the most extreme form of an allergy, and again, this can lead to shock. Right. So I discussed this in that previous presentation. Again, I mentioned HIV and AIDS, and especially how important it was to kind of see how it targets those helper T cells. And then we don't get that all important activation stage of our T's and our B's. And then that kind of breaks the immune system apart, right? So, again, this T cell and B cell stuff is a little bit more confusing than anything else that we've covered, in this chapter. So definitely spend some time on that information. And that's the reason I put this in a separate slide, is so you could just focus on the T's and the B's by themselves. All right. If you have any questions, please feel free to contact me. Otherwise, I hope you're doing well and you stay well. Thanks a lot. Have a great day.